This is the fifth and final section of chapter 3, further centres of mass, and this section is all about toppling and sliding. Now, an object which is on a horizontal or an inclined plane will either remain in equilibrium, slide either down the plane or across the horizontal plane, or topple over. And all of this depends on the angle of the incline, if it's on an inclined plane, the maximum frictional force, which is related to the coefficient of friction, and also the line of action where gravity acts in the object. So let's start with an object like this on a horizontal surface on a horizontal plane, and let's say that we have some pulling force here, P, so it's trying to pull it towards the right hand side as you look towards the screen. Let's put in where, let's say where the centre of mass is. Now the centre of mass could be in any place, but let's put it here, which means I'm going to have mg going down here if the mass of the object is m. And directly below this mg is where I'm going to have the normal reaction acting. So I'm just going to make this arrow a little bit shorter here and then put mg like this at the side, and directly below it in what I call this line of action, so imagine the line of the weight going straight down, I'm going to have the normal reaction here. Now obviously if the centre of mass was in a different position, let's say over here, then the normal reaction would be underneath. It moves with the weight. Now I'm considering a rough surface, so this is going to be rough, no smooth surfaces here if things are going to be toppling over or sliding. Which means I'm going to have a frictional force pointing in the opposite direction to the pulling force, and let's call that frictional force F, and that acts in exactly the same position as where the normal reaction is acting at this point here, which is directly below, vertically below the centre of mass. Now if it's a rough slope and I've got a coefficient of friction, so let's call that coefficient of friction mu, then the maximum frictional force is going to be mu r. Now this object will do one of three things depending on the size of P, the size of mu, and the size of r linked to its weight. So if the normal reaction r, first of all, is within the base of the shape, now what I mean by that is the normal reaction is here. We're going to look at what happens when that normal reaction is outside of it or is right on the edges of the shape. But here, the normal reaction is directly underneath the weight. It's inside the bounds of the base of the shape in contact with the surface. Then the body will do one of three things. The object will do one of three things. It will either remain in equilibrium, and it will remain in equilibrium if F, this force here, is smaller than mu r. Now we can work out F and we can work out mu r by resolving horizontally and vertically. So horizontally, for example, I will have P is equal to F, and vertically I will have R is equal to mg. So I can then compare F with mu r. It can be on the point of sliding, in which case F is equal to mu r, or it will begin to slide if F is greater than mu r, and it will start to slide towards the right in this example. Okay, so I've now changed my diagram now. I've still got a pulling force, I've still got a centre of mass, but the shape has changed so that the centre of mass lies directly above the edge of the shape. So this time the normal reaction acts at the edge of the shape or the edge of the object at this point A, which is right in the bottom corner. So then if this is the case and we've got a normal reaction acting at the very edges of the base, so that could be this side or this side on the left over here, it's doing one of two things. So it's on the point of sliding if F is greater than mu r, and it's on the point of toppling about A, which basically means you can imagine the shape is sort of trying to rotate around clockwise, and it's going to topple over with this bit hitting the ground first. So imagine it going around this way, and it's going to topple about A, that's how we describe it, if F is less than mu r. Now the reason it's toppling is because the object itself in this case, in this example, would be producing a clockwise moment about A to make it rotate in this direction. Now, the way that we're going to work out if f is greater than mu r or f is less than mu r is we're going to resolve horizontally and vertically, and we're also going to take moments about what we call the leading edge. So we would take moments, this is the leading edge here, that's the bit at the front as it gets pulled across to the right. So we would take moments about A. Now this is the last situation that can occur. Again, a new diagram. This time the weight is here above this overhang, and you can see that the normal reaction now is acting outside of what we call the contact face. Let me just highlight that. So this is what we call the contact face. The normal reaction is acting outside of that contact face because of where the weight or the center of mass is now placed. So if it's outside of the contact face, then two things can happen. If the plane is rough enough to prevent sliding, that is that F is less than mu r, the body will topple about A, and A will be the same point as before, just correcting my diagram, so it'll be there. And if the plane is not rough enough to prevent sliding, that is F is greater than mu r, then the body will slide. Okay, so now let's look at what's going on when we have a body on an inclined plane. So we'll start with this one over here, where we have the weight acting down so that the normal reaction is within the contact face of the body with the plane, and I've drawn a little dotted line here going straight down from mg, the weight where the center of mass is, and we call that a line of action. You'll see that on all of the diagrams. So here it's inside of this contact face. So if F, our frictional force here, is less than mu r, then this object will remain in equilibrium. It's not moving anywhere, it's not going to slide down the slope, it will just stay there. If F is equal to mu r, this will be just on the point of starting to slide down, and F is greater than mu r, it will begin to slide down the plane in this direction like this. Now on a second diagram, you can see that the line of action passes right through this bottom corner, which means that the normal reaction is acting through this what we call leading edge here. I haven't put on the components of the weight, they're going to be the same as they were in the first diagram. And it's similar to when the normal reaction is acting within the contact phase. Well, first of all, if F is less than mu r, it remains in equilibrium. Well, that's the same as when R is in the contact phase. Is F is equal to mu r, it's on a point of toppling before it's on a point of sliding. And if F is greater than mu r, it's going to be toppling about the point A, this point A here. So you can imagine it starting to rotate in this direction, whereas with the previous one, it starts to slide down the plane. So one's sliding, the other one's toppling. Then the last situation we can have is something like this, where the line of action goes to a point which is outside the contact face here. So you've got a normal reaction acting outside of the contact face. And in this case, if F is less than mu r, that means that the plane is rough enough to prevent sliding, then this object will topple about A. So actually it will start rotating around like this, and you can imagine this bit here starts to fall down, it's going to hit the plane. And if F is less than mu r, that means that the plane is not rough enough to prevent sliding, then the object will slide. So there's no equilibrium, remaining in equilibrium here, it's either going to topple or slide. And just like when we have an object on a flat surface, we can resolve parallel and perpendicular to the plane and take moments about this point here on the leading edge to help us solve problems. Example 19. A solid uniform cylinder of radius 3 cm and height 5 cm has a solid uniform hemisphere made from the same material of radius 3 centimeters joined to it so that the base of the hemisphere coincides with one circular end of the cylinder. Okay, so let's start by drawing out this in a diagram. Okay, so here's my shape based on a description in the question, sort of sideways view of it. Part A, I need to find the position of the center of mass of this composite body. Now, by symmetry, I know that the center of mass is going to lie on this line here. So my job is just to work out whereabouts on this line the center of mass is. So I'm placing it on a coordinate grid. By symmetry, x bar, center of mass in x direction is 0. And I've set up my table where I can start to put in the information about the separate parts, components of this 3D shape. So my two parts are the cylinder and the hemisphere. Let's start by working out the mass of the cylinder. Now the mass is the volume times by rho. So rho times by pi r squared h for the cylinder part, and that becomes 45 rho pi. And for the hemisphere, that's going to be rho times by the volume of a hemisphere. Now a sphere is 4/3 pi r cubed. Since the hemisphere, half of 4/3 is 2/3, so 2/3 pi times radius cubed, 3 cubed, which simplifies to give us 18 rho pi. Now we go on to the center of mass of each part. Now for the cylinder, center of mass of a cylinder is at its center. That's going to be halfway up the cylinder, which is going to be at a distance of 2.5 from the base. So its y coordinate basically is 2.5. And then for the hemisphere, the actual center of mass of the hemisphere, and this is in the formula book, is 3/8 from the bottom, 3/8 its radius. So that'll be a distance from here of 3/8 of 3. But since we want the center of mass from the base of the cylinder, we need to add 5 to that. So it's going to be 5 plus 3/8 of 3, and that gives us 49/8 centimeters. So now we just put the mass and center of mass into the formula. So the mass times the center of mass of the cylinder plus the mass times the center of mass of the hemisphere divided by the total masses. Now what will happen here is all the rhos and pi's will cancel out, leaving 45 plus times 2.5 plus 18 times 49/8, which is 891/4, divided by 45 plus 18, which is 63. And if we do that calculation on our calculator, we get an exact value of 99/28. So that means that the center of mass is 99/28 centimeters above the base of the cylinder. Now that's about 3.53 something centimeters. So that means that the center of mass is going to be here, put that as G, and then this distance here is 99/28, that distance from the base up to G. So moving on to part B, the composite body is placed with the circular face of the cylinder on a rough inclined plane, which is inclined at an angle alpha to the horizontal. Given that the plane is sufficiently rough to prevent sliding, part B, show that equilibrium is maintained provided that tan alpha is less than 28/33. So we definitely need to start with a diagram here. So here's my diagram. Center of mass, which I worked out in the first part, so I know that distance here from the base of the shape, base of the cylinder. I know that this angle here is the same as the angle of the incline of the plane. We talked about that before. And I've drawn the line of action, so this vertical line that goes straight down from the center of mass, I've drawn it going right through the corner of the shape. So this is the maximum angle of incline I can have where the shape will remain in equilibrium. So think about it, as this angle increases, this angle increases, this line of action begins to move outside the shape. So I want it to be inside the shape. So I want this angle alpha to be smaller than a certain amount. Now I could actually work out what this angle is. This would be the maximum angle that it can be. So the maximum angle that I can have here is going to be the opposite 3 over 99 over 28 if we're using tan. So the maximum angle of incline is alpha, which needs to be less than this maximum angle here, which would be the tan inverse of the opposite 3 over 99 over 28. If we do the tan of both sides, we get the tan of the angle equals 3 divided by 99 over 28. And so if we do that, we'll have the tan of the angle needs to be, or tan alpha needs to be less than 28 over 33. That's what we get when we do that calculation, which is what they want, so we can just put as required. Any greater than that, and then this shape would begin to topple, provided that the frictional force is enough to grip it, which means that F would need to be greater than mu r, but we don't need to worry about that on this question. Example 20. A solid uniform cube of mass m and side 2a rests on a rough horizontal plane. The coefficient of friction is mu. A horizontal force of magnitude P is applied at the midpoint of an upper edge. So you can see it's being applied from this point here, and it's going in towards the right. As shown in the diagram, the reaction between the plane and the cube comprises a normal reaction force R and a friction force F, and acts at a distance h from the lower edge of the cube as shown. So it's at a distance of h from A, and it's again shown in the diagram. Find whether the cube remains in equilibrium or whether equilibrium is broken by sliding or toppling. In each of the following cases, also determine the value of F and the value of H in each case, giving your answer in terms of M, G and A as appropriate. Now, in all three of these cases, we're going to be resolving vertically, we're going to be resolving horizontally, and we're going to be taking moments about A, since it's going to be moving towards the right. This is the point here, this leading edge, this corner here, this vertex of the cube or edge of the cube, where toppling is going to take place. It's going to topple or turn about A. So we want to take moments about A. So since we need to do the same thing in all three parts, rather than do the same thing 3 times over, we're going to write down what we get when we resolve horizontally and vertically, when we take moments about A, and then for each part we can then just substitute in the different values and work out what those answers are. So if we start by resolving vertically, I can see that there's only 2 forces, so it's going to be R equal to mg. Your action force is going to be equal to mg. Next we'll resolve horizontally, so the only forces are going to be P and F, so I can see here that P is going to be equal to F. And then lastly we're going to take moments about point A, so about this point here. I've got my little moments diagram here. So we're going to have this distance up to force P, and this distance here is going to be to A, so I'll just put that on, and that is going to be a clockwise moment there. Then we're going to have this distance to the normal reaction R, so this distance here as given on the diagram is H, so I'll just put H here, and this is also going to be a clockwise moment, so I'll just put that in there that it's clockwise. F passes through A, so there's going to be no moment created by the frictional force, but the mg, now if we bring the mg sort of down to sort of here, then we get the right angle, so that distance there, which is going to be the distance to mg. Now since this is a uniform solid cube, that means the center of mass is in the center of the cube, we're looking at the face, the side face, or one of the side faces of the cube. So this distance here is A. Yeah, so that distance from point A to the mg is going to be A, and when I say A I mean small a, like that, and this is going to be an anti-clockwise moment. So I'm writing our moments equation. If I start with the clockwise ones, so I will have 2a times by p plus h times by r, so they're my two anti-clockwise moments, and my anti-clockwise moment is going to be a times by mg. So I'm going to use all three of these equations, so I'll just highlight them here when I work out parts A, B and C. Saves me doing the same working 3 times over. So we'll start with part A, where P is equal to 0. Now if we sort of think about it, if there is no pulling force here, there are no forces acting on this cube, I'm not expecting it to do anything. I'm not expecting it to move, slide or topple. It's not going to move at all because there aren't any other forces acting on it apart from P, but we want to prove that mathematically. So if P is equal to 0, we see P in when we resolve horizontally. So that means that F is also equal to 0. And if we put P into our moments equation, so we will have 2a times by 0 plus h times by r is equal to a times by mg, and we also have that r is equal to mg, so that comes from our first equation where we resolved vertically, and that's going to lead us to the equation mg, that's r, times by h, because the 2a times by 0 is gone, is equal to mga, which gives us h is equal to a. Now what that means is that the normal reaction is within the face in contact with the plane. Actually, the normal reaction is at a distance of little a from this corner, so it's actually in line with the weight of the cube. So when the normal reaction is within these faces, so not at one of the corners, it means it's either going to remain in equilibrium or slide. Now since there is no resultant force, there's no pulling force here, it's going to remain in equilibrium, it's not going to move, and that's sort of what we expect to happen. So the cube remains in equilibrium, cube remains in equilibrium. Now normally what we'd do is we'd work out whether this pulling force is greater than F max, the mu r, but in this case the frictional force is 0 anyway because this pulling force is 0. So moving on to part B, we have P equals to half mg and mu equals to 3/4. So we'll start by putting our half mg for P into our second equation here. So we'll get F is equal to half mg, and we're also going to take moments about A, so using this equation here, this will tell us where the normal reaction force is on this base, if it is on this base at all, or whether it's in at A or outside A. Now in a shape like this that wouldn't happen. I did mention at the start where you can have a normal reaction outside the contact phase. So that may be if you had something like this and you had a center of mass, let's say at this point, it's possible for the normal reaction to be outside of this contact phase, let's say over here. Anyway, putting P and R, which we know is mg, into our moments equation, we'll get 2a times by P, which is half mg, plus h times by r. Now r is mg, so h times by mg is equal to a times by mg. So solving this equation, the mg's cancel out. This is just going to be AMG, and we've got AMG over here, so that concludes that H must be equal to 0. Now, if H is 0, that means that the normal reaction is actually acting at point A. So the normal reaction is here, right on the edge of the contact face. Now, what that means is the shape is either sliding or on the point of toppling. And the way we're going to work out which one of those two things it's doing is by comparing the pulling force with the frictional force. Is that pulling force greater than F max mu r, or is that pulling force less than mu r F max? So F max is mu r, which is 3/4 rmg. Now this means that the pulling force, which is half mg, is less than mu r F max 3/4 mg. So what does that mean? That means there's not enough pulling force to overcome friction, the frictional force, and in that case there's like enough grip to hold that base in place, which is going to cause the toppling. So the cube is on the point of toppling. That's because the normal reaction is acting right at the corner here. And lastly, part C, we have P is equal to 1/4 mg and mu is equal to 1/5. Right, so that gives us F is equal to 1/4 mg using the second equation. Taking moments, using the third equation, we'll have 2a times by 1/4 mg, that's P, plus h times by r, and r is equal to mg, is equal to a times by mg. So solving this equation here, we're going to get a half mg, and we've got a mg, or half a mg, so we've got a mg, so that means that a must equal a half a, so h is equal to 1/2 of a. So that means that r acts within the contact face, because if it's half a, I'm guessing it's going to be sort of that distance, so halfway between mg and this face here. So r and f act within the contact face. So when it's acting within the contact face, we know that it's either going to remain in equilibrium or slide. And the way we're going to decide is to compare our pulling force with F max. So since we have P is equal to 1/4 mg, F max mu r is going to be 1/5, that's mu, times by r, which is mg. So we can see from this that the pulling force is greater than mu r. So that means there's enough pulling force to get this cube moving to the right. So in this case, the cube will slide. Example 21. A uniform solid cube of mass m and side 2a is placed on a rough inclined plane, which is at an angle alpha to the horizontal, where tan alpha equals 1/2. The coefficient of friction is mu. Show that if mu is less than 1/2, the cube will slide down the slope. So here's my diagram showing everything that's on the question. My uniform cube of side 2a, the angle here of alpha, and tan alpha equals 1/2. I have the weight of the cube acting from the very center of the cube. We know that because it's uniform, center of mass is going to be at the center of it. If we're looking at the face side on, we have the frictional force here, and I've put in the components parallel and perpendicular to contain the components of the weight. Okay, so the first thing we're going to do is to resolve perpendicular to the slope, and we will have that r is equal to mg cos alpha. Now it says we need to show that if mu is less than 1/2, the cube will slide down the slope. Now, for this cube to slide down the slope, the gravitational forces, that is mg sine alpha, because there's no other forces acting on the cube, this gravitational force of mg sine alpha needs to be greater than the frictional force or greater than F max. So if we take that bit of information and actually write mg sine alpha, gravitational force is greater than the maximum frictional force. Now the maximum frictional force is going to be mu r, so mg sine alpha needs to be greater than mu r. Now we know what r is from resolving at perpendicular to the slope. I suppose what we're doing here is resolving parallel to the slope, but with an inequality. So yeah, mg sine alpha is greater than mu, and r is mg cos alpha. If we divide both sides by mg cos alpha, we'll get mg sine alpha over mg cos alpha is greater than mu. Now we'll flip that around so that we'll have mu is less than, just flip the inequality around, mg cos alpha over mg sine alpha over mg cos alpha. So the mg's cancel out. That just leaves is less than tan alpha. But in the question, it tells us that tan alpha is a half. So from that, we conclude that mu needs to be less than a half as required. Example 22. The cube in a previous example is now replaced by a cylinder of mass m with base radius a and height 6a. The cylinder is placed on the rough incline plane, which is inclined at an angle alpha to the horizontal, where tan alpha equals a half. The coefficient of friction is mu. Show that if mu is greater than half, the cylinder will topple about the lower edge. So I've got my diagram here of what's given in the question. And the only thing that's changed from the previous example is the position of the center of mass. The mass of the object is the same, the angle of the slope is the same, and in the last example what we showed was that if mu is less than a half, then we'll get sliding. But here we have mu is greater than a half. That's what's given in the question. So we know it won't slide. From the information that we had from the previous example. But it will topple if the line of action, this green line here, lies in the corner. So this point, which I'll label up as A. So if it lies, goes through the corner or outside of this contact face, then it will topple, because we know there's enough grip on this face, because mu is greater than half, there's enough grip to stop it from sliding down. So what we're going to do is a bit of trigonometry. So I'm going to draw a triangle like this, and we know the lengths of some of these sides. So this is going to be 3a, because remember, in the cylinder the center of mass is right down the center, so that's be 3a. Now we don't know the length of this here, because this line of action could be going through the corner, it could be further out from the corner. So what I'm going to do is just call the length, the whole length of this side, x, wherever it goes to. We want to find the length of x, and using some trigonometry, so we have alpha here, this will be 90 minus alpha, this will be 90 minus alpha, so this angle at the top here will be alpha. And it'll probably be helpful if I drew a larger version of that triangle. So let's do that over here, like this. So we have a length of 3a here, that's that side. The bottom one we're calling x. We want to find out where this line of action goes. Is it outside? Does it go through the corner? Is it inside? That will tell us whether it's going to topple or not. And then the angle at the top here is alpha. Now, what do we know? Tan alpha in the question is a half. How do we find tan? Tan is the opposite over the adjacent. So the opposite is x, that's that side we want to find, over 3a is equal to a half. So we can cross multiply and we will get 2x is equal to 3a, which means that x is equal to 3 over 2a. Now, what does that mean? Well, if the length was less than a, then this line of action would go through the base of the shape because the distance from the center there to the edge is a. If it was equal to a, it would go through the corner. It's actually greater than a. So that means that the line of action passes outside that contact face, and actually it passes through a distance of half a outside of the contact face, because we literally have like a length of 1.5 a from this corner to this corner, and from this part of the cylinder to the edge there is a, so it sort of extends by half a outside that bottom corner. So we can conclude that since the line of action is outside of the contact face, I should have the word face there, and it does not slide, the cylinder does not slide, the cylinder will topple. So you should now be able to do exercise 3E on pages 114 to 117 of the textbook, and there's a quick recap here. And this might be more useful than like the first slide that I did if you just want a quick way of knowing what to do. So first of all, is the normal reaction inside the contact face? We can use trigonometry and taking moments to work out that. If the answer is yes, then the body will remain in equilibrium if the pulling force that's on the object is less than the maximum frictional force mu r, or it will slide if the pulling force is greater than the maximum frictional force, so there's enough pulling power to pull it across a horizontal plane or an inclined plane. If the normal reaction is not inside of the contact face, well, if it's in the corner of the contact face, I suppose technically it's still inside, but if it's in the corner of the contact face, it will be on the point of sliding. Again, if the pulling force is greater than maximum frictional force, or toppling if the pulling force is less than the maximum frictional force. And lastly, if the line of action, well, basically a normal reaction, is outside of the contact face, it will slide. Again, if the pulling force is greater than the frictional force, or it topple if that pulling force is less than the maximum frictional force. And just a little note here that if a body is on an inclined plane with no other external forces, then P, this pulling force, is basically just the gravitational forces, e.g. or a body of mass m, the gravitational force would be mg sine theta.